So we have replaced our transistor for active biasing and for small signals with this circuit, with this equivalent AC, small signal AC model, right? And here you can see again that the basic transistor equation is still satisfying, right? Base current plus collector current is equal to emitter current, right? So if you see into the emitter to model this transistor, you will have this model, right? In which the base to emitter resistance is at the emitter side, not at the base side, right? And you have a collector, at the collector you have a current source, right? So we have come across with this one. So again, if an electronic component having a voltage and a current and has a linear relation, then it can be replaced with a resistor. Actually it would be a resistor, right? So according to Ohm's law, V is equal to IR. So at the emitter side you will be having a resistance for small AC signals, which will be equal to the base to emitter voltage by emitter, right? So now with this definition, this derived emitter AC current of this form, both are equivalent because we have just wrote GM instead of this thing. We can get the value of RE, right? So VBE by IE is equal to is alpha VT by IC, right? And similarly here, if IE comes down here, VBE by IE, then alpha goes up and GM goes down at the other side, will give you alpha by GM, right? Or if you put this alpha down to this IC, so IC by alpha is nothing but IE, right? So again, easy to remember relation is resistance at the emitter side. Small AC resistance at the emitter side would be equal to the VT divided by IE. For the case of base resistance, V was having R pi is equal to VT by IB. So IE is equal to VT by IE, right? So this resistance still in between base and emitter, about which VBE is developing, but because you are watching it into the emitter, so you would be having a resistor for this model of the transistor. For a small signal active modeling, you would be having a resistor at the emitter, right? Specifically at the emitter. It would be in between base and emitter, but explicitly at the emitter side, not at the base side. So this is a current source at the collector side, would be our output terminal as far as common emitter configuration is concerned. So value of this current source is nothing but equal to GM VBE. It means GM is the one depending on our biasing. IC by VT is GM, right? So this is nothing but a voltage controlled current source. Again, if you replace this with your IE, right? Because you have to write a relation for IC. So IC is alpha IE, IC is beta IB, IC is GMVB, right? So if you write alpha IE, why? Because you are modeling the transistor by looking into the emitter. So you want to relate this output current source with the side which you are watching, right? So it would be the emitter current. So we already know that collector current is related with the emitter current by a factor alpha. So alpha IE, right? So what is the relationship between these two things, right? We had planned to have a amplifier of this kind. We have done the DC biasing. Then we have a Q point, IVCQ, ICQ, and IBQ, and so on. And for AC analysis, we make an EC equivalent circuit. That how basically this circuit looks like for this input AC signal, right? And then we saw that this AC signal, part of this will become the AC VBE, which will be actually superimposed with the DC VBE and make some amplification for the collector side, right? And for AC equivalent circuit of this amplifier, for small signals, we have replaced this transistor, right? Either by looking into the base or by looking into the emitter. We have replaced this transistor by its equivalent circuit, or we can say model, right? So because we are looking into the base current, base to emitter voltage, so we are having a resistance in between base to emitter junction, but the resistance would be explicitly at the base side, not at the emitter side, right? So collector side we have a current source, and we have already explained everything, right? So R pi is VBE by IB for this case. VBE by IB is your R pi, right? And if we model this transistor for a small AC signal by looking into the emitter, we can replace this transistor in this circuit by this schematic or model, right? So here, because we are looking into the emitter, so we want to relate our output current with the parameters of emitter, right? So we have a voltage at the emitter side with reference to the base, right? Actually base to emitter, so it's the same, right? So base to emitter voltage and the emitter current, right? So RE is VBE by IE. So R pi is VBE by IB and RE is equal to VBE by IB. So VBE is equal to IB R pi for this case is IE RE in this case. So these all are equal. And now if we take this part of this equality, then we can get the relation of R pi with the RE like this, right? Or if we want to make both of these current similar to see what is the relation between R pi and RE, is we know that IE is equal to 1 plus beta IB. Please don't ask how this relation basically come out. We already discussed with the basic equation of transistor. IE is equal to IC plus IB, right? So instead of IE, we can write 1 plus beta IB. Now IB cancel, and we can see R pi is equal to 1 plus beta time RE. It is the same relation which exists in between base current and emitter current, right? Emitter current is equal to 1 plus beta time IB. And you can see the emitter resistance is 1 plus, sorry, base resistance is 1 plus beta time Re. The more the current in that terminal, the lesser will be the resistance at that terminal. The small the current into the terminal or out of the terminal, then higher is the resistance at that terminal as compared to the other one, right? So it has the same relation. I wrote it for the total currents instead of just AC currents, right? So for your recalling, I am writing this here, right? I is equal to IC plus IB, then I is equal to beta IB. I can write, instead of IC, I can write beta. So 1 plus beta IB is IE, right? So it means base to emitter junction. This transistor can be replaced by the small signal model of which kind? You can have this one or this one. They both are equivalent, right? Then what is the difference? Is just when you look into the base, you can feel a resistance at the base side, right? Obviously in between base to emitter, but explicitly at the base side, called R pi. But if you want to replace this transistor with this model by looking into the emitter, you also have a resistance in between base to emitter, but explicitly at the emitter side, right? And you can see both of these things are the same, because when you look here, you have actually feeling a small current, it means higher resistance. Sorry, small current, higher resistance. Is smaller than what? Smaller than this. How much is smaller than 1 plus beta times smaller than, right? So it means this resistance would be 1 plus beta time more than this one. So these both are same, right? And these models are drawn for BJT terminal currents satisfying the basic BJT equation. This one, right? Emitter current is equal to base current plus collector current. If you want to write a Kirchhoff's current law for this node, you will come up with this thing, right? Same is here. Base current plus collector current is your emitter current, right? So physically you would be having NPN material, right? But for active mode, a small AC operation, you can replace this transistor by this schematic that it is behaving like this one, that a current source is being controlled by a voltage or a current, right? So these models are drawn for BJT terminals current satisfying the basic BJT equation I already explained to you, and IE is equal to IC plus IB for small signal models, right? IE is equal to GM VBE plus VBE by R pi, right? I can replace this small AC current with the relation we have drawn, we have derived, right? And IB with the VBE by pi we have already derived, right? Or if we take VBE by R pi common, we actually come up with GM R pi plus 1, and this GM R pi is nothing but beta. So VBE by R pi into beta plus 1. And what is this? R pi by beta. You can beta plus 1. You can write it down to this R pi. It's nothing but RE. So IE is the same, right? So it means all of your model as far as your collector current, base current, emitter current, base resistance, emitter resistance, right? And conductance at the collector. It's, you can see the same relation. IE is equal to some voltage divided by the resistance. IB for small signals is equal to some voltage for that terminal of obviously and the resistance. And the collector basically is depending on VBE because of the active mode, base to emitter forward, collector to base reverse, then you have a collector current. And for a small signal, you have replaced your exponential model with this one. So it's again voltage divided by resistance, and 1 upon resistance is conductance. So you put in the form of conductance instead of resistance, right? So we call it now hybrid pi model, right? Pi because its shape is like a pie, right? And this model as T model. They both are equal, right? We already proved here, right? So why then we actually model, if they both are equal, then we would have learned only one and we need to use only that one. Why two? You will see later that one of them have advantage for some to work out for some circuits, and the other one has advantage for simplicity of working for some other case. But if you want to follow one for all the case, yes, of course you can get the same results, but with some difficulty of visualizing, not the logic, not the law of equations.